This video is about the Helmholtz Resonator and the Helmholtz Resonator element that is in SIDLAB. Starting here at the model building screen, we notice that there is a element for the Helmholtz Resonator called H-Resonator. If you want to know about the theory, you can always go to the Help menu for that element, and up will come the H-Resonator theory explaining what it is and all the relevant equations. We're not going to go through the theory right now, but know that it's there and you can always refer to it. So what we will do, though, is drag in the Helmholtz Resonator element and fill in some of the key fundamental parameters. So it requires a volume, and I'm going to use 60 cubic inches for the volume, and the neck length, which is this little neck here, we're going to use the length of 1 and a neck area of 0.3. Notice that it also asks for a main pipe area, and for that I will use 1.2 square inches. Okay, there are also some additional parameters that you can explore on your own. One of those is the added neck resistance, which we will talk about a little bit later. So now we have an element with all the necessary parameters filled in, or parameter values filled in, and we can create a model with just this simply by adding the green dot and the stopping point, the red dot, for the model. Now we are ready to go to the calculation screen and calculate the transmission loss of this particular resonator. Notice that there is one peak and nothing else. Okay, so a Helmholtz resonator, its fundamental frequency is just that. It has only one fundamental frequency, unlike a quarter wave resonator that has a fundamental frequency plus all the odd integer multiples. Now, even though we're attenuating at only one frequency with a Helmholtz resonator, in general they are more compact than other types of resonators, so that is one reason for why they are highly used. I'm also going to go back now and increase the resolution to 1 Hertz and put an ending frequency at 500 Hertz and recalculate the transmission loss. So now we have a resonant frequency of about 125 Hertz for this resonator. Now, maybe we want to line this up with a fundamental engine tone that is problematic, so we may want to move this up or down in frequency. So let's see what happens if we go back and change the volume to 30 Hertz. Okay, what's going to happen? All right, we'll go back to the calculation screen, and we will hold this graph so that we can compare it to what we're doing now and recalculate. And we'll see now that the resonant frequency has increased to about 175 Hertz. Now let's go back again and change the neck length, or reduce the neck length to 0.5 inches. Or no, I'm going to use 0.25 inches, because sometimes the neck length is simply the thickness of the metal. If, say, you're punching holes in a pipe to create a Helmholtz resonator surrounded by another pipe, it may just be the thickness of the metal, so I'm going to use 0.25 for that. Now we'll go back and calculate again. I'll notice that the frequency has increased even more, almost to 250 Hertz. Now let's reduce the neck area parameter and see what happens there. You might think that it would go up again in frequency, but we're going to reduce it to 0.2 and go back to recalculate. And notice now that the frequency has not gotten higher, it's gotten lower. And this is not intuitively obvious why that occurs with just reducing the neck area. But if you go back through the theory, you could probably convince yourself, yeah, that makes a lot of sense. Now, even though we have only one frequency of attenuation with a Helmholtz resonator, notice that, or what is often done in design is to add a series of Helmholtz resonators to get broader band attenuation over a broader frequency range. So let's do that. Let's go back to the model and get rid of the endpoint and copy with a Control-C and a Control-V. Gives us a second Helmholtz resonator with identical parameters as the first, but I will go back and change the volume of the second one to 60 again. So now we have 60 cubic inches for the volume of this, 30 cubic inches for that one. And I'll reconnect. We're going to connect these in series and add the final endpoint to the model. And I'll go back here and calculate. So now we have two peaks. This kind of makes sense. We changed the volume. Of course, there's another peak, but we have a problem because now we have a minimum here that is pretty low. So if, for example, an engine order ended up right at this frequency, you wouldn't get very much attenuation. So what can happen there? Well, how can we improve that? If we go back to the elements again, and we notice that the neck resistance is now 0. So one way of increasing resistance in a Helmholtz resonator is, for example, to add a screen, fine mesh screen in the neck. So I'm going to, just for a number, put in 0.01. We won't go into units right now on this. And then we're going to add another one, resistance in the neck of the second resonator. So let's go back and recalculate. We will hold the graph we have. So now look at what has happened by adding resistance to the neck. It has brought the minimum up to almost 30 dB, which is pretty good attenuation, even though we have given up on attenuation at some of the peaks. And oftentimes in muffler design, it is more important to bring up the minimums than it is to try to get peak frequencies matched everywhere with the pure tones or the engine orders that you are attenuating. So this ends the video on Helmholtz resonators. Keep in mind, Helmholtz resonators are for one frequency, but their advantage is that they are very compact, and if you want to broaden the frequency range, you can always use them in series.